last few years as well. And we're thrilled to have him from north of Pennsylvania. I'll let him tell you about that. Zach Barkley is a researcher at Penn State University with a specialty in measuring and monitoring methane emissions. As a recent graduate in atmospheric science, Zach used methane and ethane data from aircraft and tower networks to quantify gas leaks in Pennsylvania, West Virginia, and the South Central US. His current project involves using methane data from a tower network in the Permian Basin to understand emission trends that occurred during the onset of the COVID-19 pandemic. With that, Zach, we're thrilled to have you. I'm glad you've got a signal from your undisclosed location and you could join us today. Thank you for that, and I'll turn it over to you.
All right, nice to be here. Let me share my screen and go into present mode. So hello everyone. I'm gonna really mix things up here. I am an atmospheric scientist from Penn State University who studies the methane associated with natural gas. And so I'm gonna be talking to you today about the top-down versus bottom-up perspectives of measuring methane from the oil and gas facility. Now, I'll go on to that, but first let me give you a little bit of a warning really quickly. I am a meteorologist. I don't have any real world skills. I can't do any of that engineering nonsense that you're all talking about. So you will have to forgive me if any of my jargon related to the oil and gas industry is completely wrong. I only like point at little green blobs on a map and I say if it's gonna rain or not really. So really just have some mercy on me here. With all that said, this is methane. It's a really cool gas. I've studied it for 5 years now. It heats our homes. It's basically what it does. Unfortunately, like all great things in life, methane is a greenhouse gas, and it's a very strong one at that. It's not quite carbon dioxide levels of bad, but overall, methane increases in the atmosphere are responsible for about a quarter of all of the warming that has occurred on the planet in the last 100 years. So it's a pretty big deal in that regard. And of course, unfortunately, that is what natural gas is made of. And so there is a lot of research and methodologies done to try and quantify the methane emissions that just escape naturally throughout the process of drilling and mining out natural gas. So the main way that, at least in the US, we try and quantify methane is through what's called a bottom-up approach. And so this is what the EPA would rely on in order to calculate methane emissions in the US. And the process is really simple. Just as an example, let's take pipelines. And so what they would do is they might take measurements along a pipeline. You take, let's say, 10 measurements in total. You come up with an average emission per segment of pipe. And then you have, every industry is reporting exactly how much infrastructure they have. So you would take that average emission and you would multiply it out over the total inventory of pipes you have in the US. And using that, you would come up with a total emission rate for pipes. Now, there's a lot of components in the oil and gas industry. It's not just pipes, obviously. And so for each one of these individual components, the EPA has to come up with an average emission rate for each one of them. So they have this huge list of average emission rates and total inventory of how many of these things there are. And with this giant inventory, they're able to create and update every year an estimate of what the methane emissions are coming from the natural gas industry. When we take a look at that list and we just take it to heart, according to the EPA, the emissions primarily come from the production sector. That's probably not too surprising to people. That's where all of the oil and gas is being pumped up from the ground. So there are some leaks in that process. In particular, if you break down the production sector, the EPA says that about half of those leaks are actually coming from pneumatic devices. And my understanding is that these are actually well accounted for emissions. You have high bleed devices and low bleed devices, and there is a set amount of methane that will always escape from these devices. And so that is generally the breakdown of where we think the majority of the emissions are coming from in the natural gas industry. Now, with that said, there is also another approach to measuring and quantifying methane emissions. The EPA uses a bottom-up approach, but atmospheric scientists like to use what's called a top-down approach. And so with this approach, what you're doing is you're trying to measure the atmosphere, the methane in the atmosphere, and figure out what the methane emissions are. So in this case, what's normally done is you take a plane, you fly around a basin, somewhere upwind and downwind of that basin, you're going to have a methane enhancement. And with that methane enhancement, you can then use a fun equation up here to then try and calculate the total methane that must be coming from within the box you flew around. And so you'll get a number, and then you can attribute that to the oil and gas wells inside the basin. It's a unique approach compared to a bottom-up approach, because instead of looking at one component, getting an average and then scaling up, you're looking at everything all at once and then attributing it directly to the source. Now, the problem with this is that when all these top-down studies have been done, you get the same consistent message every single time. And that's that these top-down studies seem to show that EPA emissions from their bottom-up inventory seem to be underestimating the emissions calculated in these top-down studies, sometimes by a factor of 2 or more than that. So that's a major discrepancy here. Now, there is one fatal flaw, though, with the top-down approach. And that's that while you are indeed measuring everything inside that box that you're flying around, that can be somewhat problematic, because oil and gas wells are not the only things inside the box. You can have other sources of methane as well, including animal agriculture, landfills, and even coal mines. And these are all various sources of methane emissions that can really contribute to your overall total. And so if these are co-located with your oil and gas wells, and you're only looking at the total emissions, how can you know how much of the methane that you're measuring is actually coming from the wells themselves and not the cow that Farmer Joe may own? And so that's something that really needs to be addressed with the top-down approach, and it's a major weakness. So you've got these two different approaches. You have a bottom-up approach that the EPA is mainly in charge of, and then you have the top-down approach that you have a lot of atmospheric scientists working with, and they get two completely different answers. And for the last 5 years, a lot of it has just been back and forth between the two different groups, having conversations, polite conversations, politely disagreeing with what the total methane emissions are coming from the oil and gas industry. And so Penn State realized that this was a problem, and they deployed their finest, most handsome graduate student in order to try and bridge the gap between the top-down method and the bottom-up method, and try and really understand what the heck was going on and causing this difference. And so I was sent out to the Marcellus wells in northeastern Pennsylvania to perform a study on the unconventional wells in this region. Now, the Marcellus region in northeastern Pennsylvania is actually a really cool and unique region. I can't really say it's a new gas well region now, because it started around 2012, and honestly, that's getting pretty old at this point. But it is a newer area of gas development. And what's really interesting about these wells is that though there are not too many of them compared to some other basins, these wells are extremely high producing wells. These are your highest producing gas wells in the entire US. So understanding the methane emissions that are coming from them would be useful, since this is a huge area of production for the US. Another advantage of the Marcellus region in northeastern Pennsylvania is there's literally nothing else out there. So I'm from northeastern PA, where this study took place, and I know that the only thing out there is a bunch of of very fun people who really, it's super rural. There's no cities really. There's not even that much animal agriculture. It's very forested. So you don't have to worry about any other sources for the most part interrupting your signal. You should be only seeing methane emissions coming from the oil and gas wells. Penn State also deployed their study out here because they saw my dad as a way of getting cheap labor to go out and drive to the instrumentation and actually restart the router once a week. And they paid him minimum wage to do it, and he happily accepted. So they saved a whole bunch of money having a study out there. Regardless to say, we were very excited to study the methane emissions coming from the Marcellus in northeastern Pennsylvania. So we didn't want to do this top-down approach like every other top-down approach, because then we just end up with the same problems that every other top-down approach had, and nothing would really be learned in the end. So we're going to be deriving our methane emissions through 3 steps. The first step, we need methane observations, obviously. So we went out and we flew around the gas basin. We didn't just get 1 or 2 flights, we flew around 10 times. So we have a ton of data from a ton of different wind directions to measure this signal. And we did indeed, it was easy to spot the signal downwind each time. So we have the methane observations. The next step, and this is where we start to deviate from typical mass balance approaches, we're going to model the methane enhancements. So what do I mean by that? We're going to actually recreate the methane using a weather model. Now, before we can get into how that's done, the first thing we need is some sort of understanding of what our prior methane emissions are in that region. So recall our area of focus is these wells in northeastern Pennsylvania. And when you look at the breakdown of all the different sources in this region, again, it really is just unconventional natural gas well production. There are some cows, but it's really not a big deal. It's very small numbers. Really all that's here is unconventional natural gas. Now, I should note that in southwestern PA, there's a ton of coal. The largest coal mines in the entire US are located in southwestern PA and West Virginia, and those are major sources of methane emissions. But our thoughts were that was outside the domain. There was no reason we would have to worry about that. We're 300 plus miles away from that region. So that wasn't a big concern at the time. And I'm going to show you why that thought process was completely wrong in a bit. But what we do is we take all these different emissions and we throw them in a weather model. This is literally just a weather model. It is no different than anything that would forecast rain, clouds, precipitation, temperature. The only difference is here in this case, it's also tracking air masses that contain methane. And that's really cool. At least it is to me. Because what you can do with this weather model is you can actually put in tracers for each of the individual sources. So you can then track where would I expect a methane plume to be coming that's related to unconventional natural gas? Where would I expect plumes from coal? Where would I expect plumes from cows? And that's really helpful because that means that when we go out there and we fly around and we see an enhancement in our observations, we can then go back to the model and see what exactly was the source of it. And that ensures that when we're solving for the methane that comes from natural gas, we are indeed solving for natural gas from the wells themselves and not somebody's cow. So the final step is what we're going to do is we're going to try and optimize the natural gas emissions. We're going to make it so that we adjust the emissions in our model so that our model results end up matching our observations. And to show you that, I'm just going to show you an example of a day of how all of this works. So on May 29th, 2015, we just did a simple box around the wells. The winds were from the south, so you had winds blowing south to north. You have all your wells right here dotted in black, and you can see there is a clear enhancement downwind of the wells. So this is that same plot just turned into a line plot with the enhancements following the path clockwise around the area. So the first step we're going to do is we're going to go into the model and we're going to look at all the enhancements that are completely unrelated to natural gas. So for example, on this day, on the western side, we have animal agriculture coming from Lancaster County in southeastern PA. For those of you who are not from Pennsylvania, that's essentially Amish country. That is where all of the Amish live, and there's a ton of farming there. And so you had a plume from southern Pennsylvania actually blowing up and intersecting the western side of the flight, and that's why you see that enhancement there. So we don't want to attribute that to natural gas. Additionally, in the southeastern corner, you can see a little enhancement here. That is the Scranton-Wilkes-Barre urban corridor, a terrible place you never want to go to. And there they have a landfill that was producing that enhancement on those days. Again, we don't want to accidentally attribute these to natural gas, as some other top-down studies may accidentally do. So what we do is we then take these enhancements in the model from non-natural gas sources, and we just subtract them away. So now, assuming we did everything correct, the only enhancements that should be left should be your enhancements from the gas wells in the region. So then, finally, what we do is we go back to the model and we look at what the EPA would expect the enhancement to be from those oil and gas wells, given the numbers they have for that region. And you can see that the red line here being what the model was expecting based on the EPA numbers is way too low compared to the observations we're actually seeing out there. So all we then do is just scale it up by some linear factor until the emissions from the model end up matching the observations. So in this case, we actually scaled it up by about a factor of 2. The emission rate went from 0.13% of production, which is a really small number, to 0.26% of production, which is also a very small number, but it is double what the EPA was expecting from these wells. So let me just show you an example of why mass balances without a model can be extremely dangerous to rely on. So this is a day where winds were going from the west to the east, and we were just doing transects around the wells, and we figured as we continued to fly farther to the east, we would see larger and larger enhancements as we flew downwind of more and more wells. Instead, what we saw was that our largest enhancements were actually in the south, away from all of the wells, and that it was basically just a south-north gradient in terms of your emissions, which makes absolutely no sense given the location of the wells. However, when you go to the model on this day, you can actually see the coal plume in southwestern Pennsylvania actually blew over the region over the course of 2 days and created a large south to north gradient in the enhancement that did a good job covering up the actual enhancements we were trying to study inside this box. But we can account for that with the model. We can actually just not worry about those coal emissions at all and just solve for only the natural gas emissions. And you can see that we can perfectly match the observations that we see on this day using our weather model. And so in the end, we can actually even solve for emissions on this day where the coal was even overwhelming the source. And we find a natural gas emission rate of about 0.3% of production. So again, that number is about twice as high as what the EPA was expecting. So we did this for all 10 of our flights, and just about every day was higher than what the EPA expected. The average overall came out to be about 0.4% of production, or about 3 times higher than the EPA's number. So what we're left with now is another case where the bottom-up approach comes up with one number, the top-down approach comes up with a number that is much larger. And unfortunately, while we can have a lot of faith in the top-down approach here, this didn't really provide us any sort of information as to why we think the bottom-up approach may be wrong in this case. It just seems like we solved for everything correctly in the top-down, but that doesn't help too much if we don't know what's going on with the bottom-up and why their numbers may be coming out too low. So thankfully, the folks at Princeton decided to help with this, and they deployed these poor undergraduate students, basically had to drive in a car for hundreds and hundreds of hours to drive around wells in northeastern and southwestern Pennsylvania, and essentially just drive right up to the wells and measure the methane coming from them in a sort of semi-bottom-up approach, where they were measuring the emissions from each individual well and just they created such a huge sample of 664 individual wells. They essentially measured 1 out of every 10 wells in the Marcellus Basin so that they could definitively say what the emissions were coming from the unconventional natural gas wells. So they basically did a bottom-up approach with an obscene amount of data. So they have the answer. They know the truth. And now what I'm going to have you guys do, because I was told we want a hands-on activity, and I don't know why I listen to the people at TOPCORP, but I always end up creating one in the end. We're going to do a experiment really quickly. You're going to do your own bottom-up assessment of the Princeton data. So they provided the information on all 664 wells. They provided what the emission rate is for each one. And what I need you guys to do is go and sample 10 of those numbers that they gotten at random and create an emission factor, create an average emission rate for the Marcellus wells using 10 of their data points, and then just multiply by the number of wells there are total, 664, to create a total methane emissions from gas wells in the Marcellus region. So I'm going to actually close out really quickly, and I will share a link. Oh, here we go. I will share a link in the chat box. And if you guys could just visit that link really quickly. This is about a 5 to 10 minute project. And what you're going to be doing is you're going to be just follow the instructions on the worksheet. I did test this with a couple of people to make sure it is doable. Let me know if you have any problems, but in the meantime, I'm going to be watching your progress on this spreadsheet that you guys will inevitably be filling out. And I see someone's already gotten a head start with this. So very good. Yeah, so now we're going to have, I guess, 5 minutes of quiet time, but people can talk and converse and ask questions while you're working on this quick project. And I do understand that some of you will be unable to do this, the people on their phones in particular. That's fine. I actually, so long as 10 of you do it, the point will be made. You'll see what happens here. This is basically just statistics 101 with a fun lesson at the end. While that's going, I did see something in the chat box. I know there were some people from the EPA here. Yeah, I should have planned for some sort of music or entertainment during this process, but I wasn't sure what to do. I kind of just wanted to watch the numbers come in. Oh, Claire, you're trying to copy and paste. You're going to get the black. There you go. Once 10 of you have finished, I will plot up the results, or before 10 minutes elapses. But I think we'll have 10 results in before 10 minutes elapse. Is anyone running into difficulties?
Hey, it's Kate, and I don't know if it's just access being in another country or what, but I can't actually see any numbers. It's just like a big column of black.
Oh, no, that is correct. I didn't want people to be able to see the numbers themselves. If you click on a number, if you click on one of the columns and then just look above.
Okay.
Yeah, it'll tell you what the number is. If I revealed the numbers, it would reveal what the big problem is already. So I'm trying to keep them hidden for the time being.
Okay.
I didn't know. I was stuck because the first number I got was a 0. So I was like,
No, that's fine.
So I kept doing it, and I was like, maybe I'm not doing this right. I was like, how's everybody got these numbers? So I got stuck for a second.
Yeah, about I think a fourth of them. No, I don't know about a fourth, but most of them are very small numbers. Usually when you're driving by a well, you don't actually see that much emitting from it. Most of the wells are operating properly. So yep, that's correct. Evan, did you really draw the 625? That's gonna, okay. 213 is scary too, but this only works if all of you draw the correct numbers. If you guys draw the wrong numbers, then my point is completely gonna blow up in my face, and I'm just gonna feel silly at the end of this. So I'm counting on you guys to really follow statistics here and come up with the average I would expect. Oh, I see what you're doing, Evan. Very clever, drawing your random numbers right here, using code. Overachieving.
They seem to continuously randomize this. I don't know if it's going to work.
They always change every single time you do any sort of action, which, you know, it's not a problem, but it is really irritating. John, what time does my session end? Because I want to leave 10 minutes at the end to talk about the results, or maybe 5 minutes.
Right about 4:40.
Okay. All right.
Sound good,
Give you
Zach?
guys 5 more minutes. I promise the end result is cool. Wow, Keith, you really like your zeros there.
I know. That's why I was wondering if it was working right.
You're getting zeros and then you're getting giant numbers. You're getting all the extremes there. That's fine. It's working. It's random chance. You guys are starting to worry me here. You're drawing some big numbers. All right, well, I can still make a point. It just might not be the right point. All right, well, time to start plotting up the data. Sorry, ignore the chart. Pretend you see nothing. There we go. Let's move this over here. Edit. Hmm. All right, 3 minutes. I believe in you guys. Evan, I think you tried to be too clever here.
I'm paying for it now.
2-minute warning. All right. I'm gonna help here. Actually, no, we're just gonna cheat. We're gonna drag. Fill in these last bunch. Very good, very good. Fill this in. No, I don't want years. Never mind. We're not gonna calculate years. Okay. All right. So let me take a screenshot now. Wow. Geez, you guys were all measuring the same thing, right? Oh, shoot, one of you finished. Hang on. Okay. Let me paste the results and then we will go back to the presentation. And let me put the truth in here too. It's actually like this right here. All right, I'm going back. Thank you all for participating in your bottom-up study. Remember, while there are many bottom-up estimates here, the EPA only has one chance at it. So they would not have all these different attempts. They would only have one number and they would have to trust that that is the correct number. So what you can see here is a couple of things. One, you have wildly varying estimates here. And they actually seem to fall into about two categories. One category is numbers that are very low. Keep in mind the red is the truth here. So one is numbers that are anywhere between half of that to about a fifth of that, or even in this case, like a tenth of that value. So those would end up wildly underestimating the emissions. In the other cases, you have these numbers that are like way higher. They're maybe 2 to 3 times higher. than what the EPA, or sorry, what the actual truth was in this case, which was the red bar. So very few people actually got anywhere close to the truth here. So what the heck happened? Well, so in order to really reliably do any sort of bottom-up estimate where you're coming up with an average emission per device, it helps to assume that your emissions are Gaussian or a bell curve in their distribution shape. And so basically you would assume that, you have a typical emission value for each component, and, maybe some might be a little bit lower and some might be a little bit higher, but they follow some sort of easy to follow curve that's well understood and is not very complicated, like most things do in life. However, that is not how most emissions work in the oil and gas industry. This is the actual distribution of the well emissions that you were sampling from. And you can see that indeed many of the wells are very low in terms of their emissions. And it seems to follow a normal curve at first. But then what happens is you have wells that just have huge emissions to them, and there's no end to it. It's just, you have wells that, let's say you have one that's 38 kilograms per hour. That single well is emitting the same as all of these wells over here in terms of its total value. But these wells don't happen that very often, these huge emitting events. So when you're sampling, if you only have a very small sample, you're much more likely to capture a lot of these lower samples, these lower emitting samples rather. And in the case where you do get a number that's, let's say, as high as 360, if you're looking at your data set and most of your numbers are like 0, 0.1, 0.2, and you have a number that's showing 360 kilograms per hour, you would probably throw that data point away because it doesn't look representative of the rest of your well emissions at all. So what ends up happening at the EPA, and with actually any bottom-up inventory, I'm picking on the EPA here, but this is just a fact of life with statistics, is that you end up oversampling low-emitting wells and components and devices, and that ends up leading to numbers like was calculated here, where you have values that are much lower than the actual truth. And again, if you do have one of these samples that's a lot higher, that's because you likely drew one or two wells that had huge emissions coming from it that didn't look representative of the rest of the sample. So these would likely never exist. They would likely be thrown out as bad data points. So in the end, bottom-up inventories that are following a curve of data that have this long tail distribution to it really cannot be used to capture the overall average emissions of various components in the industry. And just to emphasize this a little bit further, in that data set you just sampled, half of the emissions were only coming from 2% of the wells. So roughly 98% of the wells really had nothing to do with the overall total. It was just 2% of the wells in the end that mattered. So it was really just a case of, did you accidentally sample those two wells or not? And then just a simpler analogy of what these super emitters are and how they work. One way to think of this would be just filling your tank on any individual day. Yeah, sure, some methane or some gas escapes out when you're filling your tank. You can smell it. It's there, but it's not a big deal. It's a tiny amount. And every day, thousands, hundreds of thousands, millions of people are filling their tanks, and you have a tiny amount escaping out. And you could measure that tiny amount, and you could come up with an overall emissions from those millions of people filling their gas or filling their cars every day. But what if you have one case out of every 1 million where something just goes horribly wrong? That one case could emit more than the millions of normal cases on any individual day. And so you're not going to be sampling, when you're out sampling the field trying to calculate how much is leaking out of these car emissions, unless you have really bad or good luck or whatever you want to call it, you're not going to capture an example where something goes horribly wrong. You're probably going to be capturing very normal circumstances. And so it's the same with the natural gas industry. You have accidents, you have malfunctions where something goes wrong and you just have gas spewing out. And those events are not going to be captured by a bottom-up inventory, but in truth, they're probably responsible for a large portion of the emissions. And so that's where the top-down study has an advantage. It can't see any one individual event, but it can see everything that's happening in the basin all at once. And in the end, it's going to capture the good and the bad that's occurring throughout the different components in a given basin. The problem being it can't then pin down what the root cause of the incident is. So my main point here is that for bottom-up inventories to work, we need to somehow find ways to be able to account for these large events that otherwise are not captured by a bottom-up inventory. And that is really the key to really understanding what the true methane emissions are in the US. And so I'm going to end this talk with 3 potential avenues for the natural gas industry to potentially eliminate methane emissions. The first one is obvious: target known emitters. The bottom-up inventory may not be perfect, but it is still a huge source of data, and we know so much about emissions from the various components, even if we are missing some key components in it. And so from that data set, we can figure out which emissions are the largest, or which ones are the easiest ones to target in terms of emission reductions. Can we maybe switch over from high bleed to low bleed devices? And in fact, this is basically the main way we are reducing emissions from the natural gas industry. We are working with the bottom-up data set, and we are targeting the high emitting devices that we know exist, and we're reducing them. Where we could also be reducing emissions, though, that is not getting much focus, is the target of super emitters or malfunctions. If they really are responsible, if the bottom up and top down are about off by a factor of 2, then it can be assumed that these super emitters are roughly half of your emissions. So if we can find a way to quickly detect any sort of malfunction that would lead to a large amount of methane spewing out into the atmosphere, we could potentially reduce emissions by up to 50%. And furthermore, this is money that's leaking into the atmosphere. I am sure companies would love to be able to detect and fix these leaks immediately as soon as they happen, or even before they happen. So that is a goal that is being worked with different industry members now to try and focus on targeting these malfunctions. The primary ways of targeting these days is through drones and through satellite technology. We now have satellites that can actually measure methane from space. So eventually we hope they'll get refined enough that we can actually see leaks at an individual level. And then finally, I didn't talk about this in this talk, and let me see if yes, I have 1 minute. Let's go for it. One final way we can reduce emissions, and I heard it talked about a bunch here actually, your concerns regarding orphan wells. In general, there's actually a large amount of emissions that come from low producing or non-producing wells. About 25% of emissions in the US come from wells that are producing less than 10,000 cubic feet of gas per day. These wells are responsible for less than 1% of the gas produced in the US, but they're responsible for 25% of the emissions, mostly because they're just inefficient, they're not taken care of. So really, if we can find, there's really no need for these wells to exist. If we can focus on drilling higher producing wells and work on plugging lower producing wells, that is an easy way to reduce emissions. Now, who's going to get the money to plug hundreds of thousands of low producing and abandoned wells? I don't know. There's your practicality problem right there. We just don't have enough funding to do that sort of project. But these really are 3 different approaches that can be done to reduce methane emissions from oil and gas and make the world a happier place. And with that, I end my presentation and I turn it over for questions.
Thank you, Zach, and we're all happier. Thank you for that. Great. And you know, maybe as I look here at the time, not to short Zach of questions.
No, go ahead.
No. But I know Dave is still with us, and what I would ask is that as we come to the close today, and we've got a little bit of time that we were saving just specifically to ask questions of Zach and Dave, of our presenters. I don't think Araj is with us, but particularly Zach and Dave, if you have got questions, this would be a great time to fire them at them and get any clarification or anything lingering in your mind that you'd like to clear up. So go to it for Zach and Dave here.
Zach, I got a quick question for you. In our area, we got a lot of mostly water-driven fields, but we do have some gas-driven fields.
Where is your area?
Kentucky,
Okay.
Western Kentucky.
Gotcha.
We're in the Illinois Basin where I'm at. Eastern Kentucky's got the Appalachian Basin over there. I don't know too much about them over there. They're on the other side of the sticks. But so we do have some gas-driven fields, and there's several leases, actually not too far from where I live, that used to provide all the natural gas for a neighboring city about 40, 50 years ago. Well, that has since ceased operation. You have a few producers out there that are still operating, but pretty much they flare the excess gas because there's no longer enough for commercial value. Do we know, I guess, how we would track the emissions from wells that are operating, however, don't have enough gas for commercial value, and so therefore it's either vented or flared?
Yeah, so I don't want to speak for the EPA here too much because I know the EPA is on this call. But wells generally in the bottom-up inventories are roughly treated the same in terms of their emissions. So a well that's really just being, the gas is just being flared out is probably going to be listed at a similar emission rate as wells that are producing hundreds of thousands of cubic feet of gas per day. So in that regard, that's how they would be accounted for in a bottom-up inventory. They would be treated the same way. Obviously, in terms of their actual emissions, they probably behave very differently. And a lot of it depends on the condition of the wells themselves. And also the efficiency of the flare, because flares are not 100% efficient. You have some gas that escapes out of them. Generally, low producing wells do not make that much methane simply because, you know, you have a limit on how much methane can actually escape into the atmosphere. But it's the sheer number of them that end up leading to their rather large contribution towards the total methane budget. So it becomes hard to want to actually spend the time to quantify a few hundred or so low producing gas wells that would be used for that purpose. But they are part of a broader problem in terms of the overall emissions.
Do you have much luck having interoperability between different divisions? Like for us, Division of Oil and Gas is separate from Division of Air Quality or Division of Water.
Every state is different and it's a nightmare.
So, you know, I don't even have a way to track the emissions. So when I'm putting wells up for bid on wells that's been forfeited, you know, I know where some abandoned gas wells are that are leaking.
Yeah,
But
so
I don't even know where I would put that in my plugging program as far as priority, because I can't measure
yeah.
what this is, as opposed to something that's leaking oil near a waterway. That's going to have a higher priority.
Right. So individual states have their own metrics in terms of what they report. In the end, no one actually, states usually do not calculate emissions from their own wells. What they do is they have the inventory, which they then send up to the EPA, and the EPA uses that and their spreadsheet to calculate what the emission rate would be for a region. So you can't really get emissions from any individual gas field or anything. People have used charts and graphs to try and scale it down to have some sort of resolution, but it's just an algorithm. It's not, people aren't actually measuring the true emissions of oil and gas basins on every given day. It's usually some specialized study like my own that's flying around a basin, and those are done maybe once or twice a year.
Out of curiosity, like some operators around here have put in vapor collection systems on their tank battery sites. They're pretty rare in my area, but Indiana and Illinois, just across the river from me, tends to have more of them.
Yeah.
Does it seem like those help decrease the emissions, or has there been a way to quantify that yet?
So theoretically they should, and the EPA's database accounts for how many emission reduction components that you've installed. So you're providing a total number to the EPA with that, and that will be subtracted off from your total. Interestingly enough, because technology has improved in that regard and more regulations have been put in place, the total emissions in the US from oil and gas have actually been calculated to decrease in these inventories over the last 10, 15 years, despite oil and gas production doubling during this period. And that's simply because we're not drilling too many new wells. The wells that we can drill these days that are unconventional are super high producing. So they're nothing like the hundreds of thousands of older conventional wells. So overall, we don't add that many new emissions from the EPA's inventory, but we add all these new emission reduction techniques that end up subtracting off from the inventory. The long story short, those are accounted for in a bottom-up inventory process, and we have a general idea of how much those emissions should be reduced by.
Okay, thank you for your time.
It's not so much a question, more a comment. I'm actually just finding it interesting reading the chat and stuff like that, where people are saying like, oh, the government should subsidize plugging these wells and that kind of thing. So here in BC, it's a little bit different. We recently came out with a methane reduction regulation, which actually requires operators to do their own testing, basically for fugitive emissions on all their upstream assets and that kind of thing. And they have to submit it to us. And then operators that end up having lower scores as a pattern gradually have to test less, whereas operators that have not as good of scores have to test more, and they do have to be under certain levels, that kind of thing, change out certain equipment. And it's very specific on how much each different kind of equipment is allowed to emit. And it was pretty strict. I haven't had to deal with it a lot because I moved and now I do more downstream and major project stuff. But so I haven't had to deal with that regulation a lot, but it was a huge improvement for us. And oil and gas companies typically took to it quite well, which was great. And then in combination, we actually also just had a brand new dormancy orphan well regulation come in. So we charge fees and levies basically to companies that go into an orphan well fund. And then when wells go into the orphan well fund, we actually have a group that does the restoration and such on these orphan wells. And they use the money that's provided by industry to restore all these wells. So it's not actually coming out of our taxpayer pot. And I think the turnaround time is generally, I know it went up, but it's still less than 10 years, I believe, for all the wells to be completely reclaimed and such, which helps a lot on that side. So in combination with the methane reduction regulation and fugitive emission stuff, combined with the orphan well fees going up and security management stuff, it's been a really good combination here in BC. And yeah, it's been very interesting to see how that's all going.
Now, if you talk to the people in Pennsylvania, it varies state by state in terms of regulations regarding orphan abandoned wells plugging. It was funny, I went to a whole conference on it, and the poor people in PA, we get no money to actually plug our wells, and there are hundreds of thousands to millions of abandoned wells in Pennsylvania. And they just, there's not enough fees that come from the oil and gas industry here to actually plug them. So they work as hard as they can with this team of like, I don't know, 10 people to plug like maybe 3 or 4 wells a year. And it's rough for them. And so I do see that open a can of worms comment. Yeah, it would be nice to subsidize plugging wells, or rather to put more money towards that. And God knows that they need it out here in Pennsylvania, in particular because it's a hazard to people who are building buildings or finding out that their buildings are on top of orphaned or abandoned wells. But just to attack you here, I'd point out that wind farms long-term are probably going to actually reduce emissions a lot more than plugging wells. So I'm fine with the subsidizing wind farms too. And pay attention here, pay attention here to the EPA people here, because they're providing much smarter and more detailed information on what the EPA actually does rather than just some random scientist perspective. So take their advice at heart too.
Thank you, Zach. We do have time for a couple more questions if there are for Zach and Dave.
Yeah, I had a question and comment, Zach. First off, presentation was great and the activity was fun, so thanks for that. In terms, so I do a lot of work with orphan wells out of Texas, and like right now there's, I think there's 6,000 orphans, like legitimate orphans, where there's no operator around to take care of them. So whenever you're saying like the emissions and methane come from these wells, it's just like the fittings are getting old. And then I'm sure there's probably a correlation between the age of the well, because we've got wells, 50 years old that haven't been touched, since then. So is it mostly just like the connections of valves are just kind of going bad, and it's such a small leak you wouldn't notice it unless you're like had a sensor on it to try and catch that?
So it's interesting, and the message is actually a lot more nuanced than I put it in that 5-second segment at the end. Orphaned and abandoned wells generally actually don't emit that much at all. And it's hard to quantify them because, most of them, the locations are very not known. You can't just fly around a field of orphaned and abandoned wells and measure them using a top-down approach. They're really a pain to quantify. It's actually the emissions from lower producing conventional wells that are still tracked that end up really contributing to the overall total. Because in general, just my understanding with when you're running a well and producing from it, you have processes that are always going to leak out some small amount of methane associated with it. With the high producing wells, if you have a little blip that comes out, who really cares? Because you just produced 10,000 times that blip, and really the overall efficiency is great. But with all these very low producing conventional wells, if there's a little gas release, that might be as much as 10% of your production right there. 1 to 10% of your production. And there's just so many of these older but producing conventional wells. There are hundreds and thousands of them. And so it may not even be a maintenance thing. Honestly, the maintenance thing might make them even worse than what the industry, what the EPA would calculate them to be in a bottom-up perspective. But just in general, just based on how they work, if you are producing very little gas and you're releasing about 10% of it into the atmosphere, even if it's not that much, it just adds up. And it's like, why does this even exist when we can make a well that's producing 10,000 times more than this well right here release the same amount of gas? So it's a problem of legacy, not necessarily legacy wells, but just these older wells that we relied on that still exist that don't really need to exist anymore. But of course, plugging hundreds of thousands, and someone is still profiting from these wells, or else they would not exist. So it's hard to get the money or the motivation to address that part of the issue.
Thank you, sir.
Zach and Dave, thank you for your presentations. Thank you for being with us, hanging in there with us all day and participating. I hope that next time I see you, that it's in person and we are in front of this this group.
This is better.